Hello, geometry friends. This is the last video I'm going to do on differential forms. I have learned enough that I'm comfortable understanding the basics of it. I was just curious, that's all, because when you're studying Riemannian geometry, you run into uh, a differential geometry all the time. There's so much of it on YouTube, all over the internet. I was just curious, so I've learned enough that I'm satisfied to move on. I hope you did too. After this, I think I'm going to do like a wrap up. We'll call it a crash course or something, where we just put everything we learn in one format in one video together, so we can always use it as a reference to go back if we need stuff. Okay, so let's get cracking on this one. Okay, let's start with vector calculus. Oh, the name of it is Stokes theorem using vector calculus and then differential form. We're going to compare these two things. We'll start with vector calculus because that's what we're all very familiar with. So the Stokes theorem relates the surface integral of the curl of a vector field over an oriented surface S to the line integral of the vector field around its boundary delta S. It's a lot of words. And the horrible looking equation, I'm sure you've seen this before, looks like this. We're going to start with the left-hand side and see what it equals to a real simple example. Then we'll do the right-hand side, okay? So our vector field is just this, very simple, and it is a circular rotation about the origin. That's all it does. Okay? Now our surface S will be the upper hemisphere defined like this, where Z is greater than or equal to 0. And the boundary del S will be a circle in the XY plane. So it's going to look like this. Okay? So here's our upper hemisphere. This is our manifold. And here's our circle. And I put a tangent, the vector on here, which is pointing in that direction, which implies that we're going in a counterclockwise direction, which implies a positive. And that's important in differential the forms, but also in this because we want the normal to stick straight out, right? If this was going the other way, the normal would stick down. Okay, we want to compute the curl. We all know how to do this. Here's our basis vectors. Here's our del operator. Here's our vector field. And that just gives 2ez. All right? Now, the normal vector in this case is always pointing in the z direction, like I said, because that's what I chose on the manifold. The easiest way to do a normal for me is just to say e theta and e phi basis vectors are tangent to the surface at every point. Then the normal is just e theta cross e phi. And since we have a unit sphere, that's really easy. It's just ez, right? It looks like that. So everywhere on this manifold is pointing straight out. Now we need NDS, where ds in our case is the area of the boundary. This is the area of the boundary, and ours is just a circle. So what's the area of a circle? It's just pi r squared when r is equal to 1. Okay, so NDS just becomes a pi because r is equal to 1. It's a unit circle, EZ. That's it. All right, so we performed this del cross F. We did. Here's NDS. We dot them together. EZ is 1. Let's just get 2 pi. There's no integral left to do. Okay, now let's do the other side, which is this. Now, to do this, we want to parameterize our unit, the circle, with r and theta. We've done this many, many times. So r of r and theta is equal to this, but r is equal to 1, right? So we're just left with one parameter, r of theta is equal to this, and we want to go from 0 to 2 pi. So the dr now, so we take the derivative of this with respect to theta, that's all we got. We get this, and f dot dr, then we put in what y is. Y is r sine theta, but r is equal to 1. And x is r cosine theta. Here's x. But r is equal to 1. We dot those two, and we just get 1. So that was simple. So our integral is really easy. It's just the integral from 0 to 2 pi of what we got, 1 d theta, and it's just 2 pi. So it agrees with the thing above. Yes? Okay. Stokes' theorem in differential forms. This is the meat of what I'm trying to get to. Here's a bunch more words. Differential geometry generalizes Stokes' theorem and unifies the fundamental theorem of calculus, Green's theorem, remember that, and the classical Stokes theorem, that's what we did above, into a single equation for any smooth K manifold, capital Omega, and a K minus 1 form, little omega. So if this was a two-dimensional manifold, like the surface of a sphere, then this would be 2 minus 1, a 1 form, okay? And the equation looks like this. And it looks really intimidating, but it's really not that hard to use, especially for our very simple example. Okay, we're going to do the right-hand side first. I don't know why I changed, but I did. So in R3, omega can be a 0 form, a 1 form, or a 3 form. And capital Omega can be the path in 1 dimension, could be the surface in 2 dimensions, or a region in 3 dimensions. All right, so that's the separation of those two omegas. Now, since our vector field was this, the equivalent 1 form is just that simple. And remember, we're in Cartesian coordinates where vectors and covectors, vector fields and covector fields are the same thing. This is not true in curvilinear coordinates. So be careful, it's not true. Compute the exterior derivative of our 1 form, okay? So here is the exterior derivative of our 1 form. Remember, you take the exterior derivative of the function wedge dx, exterior derivative of this function wedge dy. Now, when we take this derivative, we have to do it over all of our coordinates. And our coordinates are x and y. So derivative of that with respect to x is 0, derivative of that with respect to y is minus 1. Then we have dy wedge dx. Derivative of this with respect to 1 with respect to x is 1 dx. With respect to y is 0, so we get 1 dx wedge dy. We flip this one, which gives a negative. That negative cancels that one. We're left with this equation, which is just, here's our 2 form. Okay? Now we take, and we've already done this, but we parameterized x and y. So we need dx and dy, right? So dx, we're going to take the derivative of this with respect to r, and derivative of x with respect to theta. Here we take the derivative of y with respect to r, derivative of y with respect to theta. Okay, we plug those back into our 2 form, and we get r dr wedge d theta. Okay, now, and we put that back into our 2 form, which has a 2 here. So here's our entire equation. Now remember this, r dr wedge d theta is actually the square root of the determinant of the metric tensor in the coordinates dr wedge d theta, which is the area form. So since the r is already there, because that is the square root of the determinant of the metric tensor in polar coordinates is r. So this just becomes our area element, as we would in tensor calculus, okay? So we just integrate this. We have a double integral from 0 to 1 for r, 0 to 2 pi for the theta. We integrate this, the 2's cancel. We plug in our 1. We just wind up with d theta equal to pi. That's it. And that agrees with everything we've done above. Okay, now we're going to do this side, which is even easier. So here is our omega, right? This is our 1 form. Once again, we parameterize this with x and y, r and theta. So dx is just a derivative of this with respect to r, derivative of this with respect to theta, derivative of this with respect to r, derivative of this with respect to theta. We plug those back in to our omega, and we get, since we have a unit, the circle, r equals 1, we just wind up with d theta, right? Because this since it's negative, cancels that, and we're just left with negative times negative is positive, and we wind up with r times cosine squared theta and sine squared theta, which is just 1. Since r is 1 also, the whole thing just becomes d theta. So that is a really even integral, even I can do. Okay? So the whole point of this was to show that uh, how this is done in differential geometry uses the unified Stokes equation, which is this. Okay? And there's obviously many, many more powerful examples of this. I just chose a very simple one. All right, thanks for watching.